I think we can start. So welcome back for this thesis session 1. So it's a quite packed schedule. I mean, there are 8 presentations. So for next 2 hours. So I will request all the speakers to please complete your presentation in 12 minutes and give 3 minutes for question answer to thesis judges. So we have 4 thesis judges: Professor Bhalchan Joshi, Professor K. Indulekha, Professor Mosmi Das, and Professor Durgesh Tripathi. Okay, so let's start with the first speaker, Barnali Das. She will be talking about coherent radio emission from hot magnetic stars. So Barnali, I will give you, warning at 10 minutes, and then
sure.
Wind up at 12 minutes. Okay?
Yeah.
Thanks. Go ahead.
Yeah. Hello everyone, my name is Barnali Das and I recently completed my PhD from the National Center for Radio Astrophysics, Tata Institute of Fundamental Research, under the supervision of Professor Poonam Chandra. The title of my thesis is Coherent Radio Emission from Hot Magnetic Stars. So when I said hot magnetic stars, I meant stars of spectral type O, B, or A that are characterized by the presence of large-scale surface magnetic field, which are often of kilogauss strength. In these stars, the interaction between their strong stellar wind and their large-scale magnetic field, which have been found to be dipolar in most cases. So this interaction leads to the formation of a co-rotating magnetosphere. And this magnetosphere hosts a variety of electromagnetic phenomena, which leads to production of X-ray emission, H-alpha emission, radio emission, etc., etc. So the one in which I'm interested in is the production of radio emission. The non-thermal radio emission from solitary hot magnetic star was first discovered in 1987, and it has been known since then that the dominant source of magnetospheric radio emission from solitary hot magnetic star is the gyrosynchrotron emission. So in these stars, there are sites in the magnetosphere where magnetic reconnection takes place, and this energizes some of the stellar wind electrons, and then these electrons then emit in radio bands by the process of gyrosynchrotron. But in the year 2000, a new kind of radio emission was discovered from a hot magnetic star CO Virginis. So this new kind of radio emission was different from the gyrosynchrotron emission in several aspects. So here I am showing you the 1.4 gigahertz light curve of the star at for total intensity Stokes I and circular polarization Stokes P. The x-axis here is in units of rotational phase. So 0 to 1 is basically one rotation cycle of the star. It's essentially time. And this panel shows the line of sight magnetic field variation as a function of rotational phase. So as you can see, there are certain rotational phases at which the flux density got enhanced by nearly an order of magnitude. And at these phases, the flux density, it was found to be close to 100% circularly polarized. Also, these enhancements were confined to a narrow range of rotational phases. And these rotational phases were almost coincide with the zeros of this line of sight magnetic field. So based on all these properties, the emission mechanism was identified to be the electron-cyclotron major emission, in short ECME. So ECM is produced near the orbital region of a star. So this is a cartoon diagram. This is the dipole axis, and these are produced in ring-shaped regions near in the orbital region, and these are called the orbital rings. And one important property of ECM is that the frequency of emission is proportional to the local electron gyro frequency. As a result of that, the higher frequencies are produced closer to the star, and vice versa. Now, to produce ECME, there are two key requirements. One is the magnetic field, and other is the energetic electrons with an unstable distributions. Now, these hot magnetic stars, they have strong stellar wind, which acts as a source of electrons, and they have this large-scale magnetic field, which, in addition to fulfilling the criteria of magnetic field, it also creates a condition where an unstable electron distribution can be produced. So, taken as easily satisfy both the key requirements of ECME. Thus, it was not really a surprise when a hot magnetic star was found to produce this ECME, which is a coherent radio emission in nature. But what was surprising was that between 2000 and 2017, CO Virginis remained the only confirmed hot magnetic star to exhibit this phenomena. So the lack of any other discovery within such a long time naturally led to the consensus that ECME is an extremely rare phenomenon among the hot magnetic stars. But the problem was that C Virginis didn't appear to be special in any sense. So is it indeed rare? If yes, then why? The same issue, the fact that there is just one star exhibiting a particular phenomena, it stalled the progress of the field. So little was known about the phenomena itself. For example, it was not known how it is related to stellar properties, what is the frequency range of operation, etc., etc. So this limitation motivated us to take up two projects. One was to conduct a systematic search for this phenomena, which we hope that will enable us to address the question of how rare the phenomena is. And the other was to observe the star over a wide range of frequencies to explore the frequency dependence of the property of this phenomena. We also realized that the past searches had been almost entirely confined to gigahertz frequencies. There was precisely just one search conducted at sub-gigahertz frequency, but that was only over in very narrow rotational phase ranges. So we decided to explore a new phase space by conducting our search at sub-gigahertz frequencies using the upgraded Giant Meter Wave Radio Telescope, or UGMRT. For our wideband study, we decided to observe stars over 0.424 gigahertz using the UGMRT and the Karl-Jasinski Very Large Array, or VLA. The reason that we didn't want to go above 4 gigahertz because there were already several high-frequency observations which showed that those stars do not produce ECME at those frequencies. And the result from our first project is that we discovered 11 hot Mendic stars that produce ECME, and with that, the current number of such stars has become 15. And we have also coined a name for this class of stars, which is the main sequence radio pulse emitter, in short MRP. And now that we have a reasonably large sample of stars, we could attempt for the first time to find a relation between the ECME property and the stellar property. And we found that the tightest correlation was found between the ECME luminosity and the maximum surface magnetic field strength, which is called B naught max, and the stellar effective temperature. And based on the observed correlation, we constructed a quantity which is of this form. We called it as X factor. And it's curious that there is this T effective minus 16.5 whole square. It seems like stars which have temperature around 16.5 kilokelvin exhibits the strongest ECME. But I would like to emphasize at this point that this relation was derived using just a small number of stars, and we really want to find out whether this is a robust relation or not by considering a larger sample in the future. Also, the same project enabled us to find one very important inference, which is that now by considering stars which are in the same physical parameter space, we concluded that at least 32% of the hot Mendic stars are MRPs, which completely ruled out the notion that ECME is a rare phenomenon among the hot Mendic stars. Under the second project, we observed 3 MRPs over this wide frequency range, and we found that all 3 of them exhibit properties that were inexplicable based on the existing ideas. Let me now give you a glimpse of what I mean by existing ideas. So this is a star, this is a cartoon diagram, and there is this inner magnetosphere, which is the region that contains the closed magnetic field lines. It also contains confined magnetospheric plasma, and hence supposed to be the densest part of the stellar magnetosphere. So ECM is produced near these magnetic poles, and when it enters this inner magnetosphere, it suffers a refraction. But after that, it essentially moves in a straight line because any other density gradient is considered to be negligible. And the lower frequencies will deviate higher than the higher frequencies. And if this scenario is valid, then this is the kind of frequency dependence that one would expect for ECME, which is that, so here basically the two colors represent the ECME coming from two opposite magnetic poles, and observationally they can be distinguished because they will have opposite circular polarization. So the only effect of ECME should be that the gap should decrease as you go to higher frequencies. But this is what we observe. So I am giving just one example for the star Cu Virginis. And if you compare them, you can already see the differences. For example, just compare this light curve and
Barnali, you have 1 minute.
Okay. And this made us question the existing scenario, and we decided to investigate the role of inner magnetospheric plasma by developing a 3D framework. And we indeed found from our simulation that there is very strong frequency, there is strong role of the inner magnetosphere, which caused significant deviation from this prediction of the single refraction model. So our conclusion was that the inner magnetospheric plasma can impart strong frequency dependence in the observed ECME characteristics, which gave the idea that ECME might be useful as a stellar diagnostic. With that, I would like to summarize. So we conducted a first sub-gigahertz survey, and which result for ECME, and it's resulted into 11 new discoveries constituting 70% of the current sample, and also enabled us to infer that ECME is not a rare phenomenon among the hot magnetic stars. We identified magnetic field and temperature to be the two stellar parameters affecting the ECME luminosity, but we'd like to validate it with a larger sample. Finally, from our wideband observation, we found strong frequency dependence, which suggests that ECME, the inner magnetosphere, plays a very important role, which led to the idea that ECME could be a stellar diagnostic. But to achieve that goal, we'll have to characterize the relation between the observed property, ECME property, and stellar physical property via both wideband observation and modeling. And this is the list of publications that came out of this work. And yeah, that's where I'd like to end. I hope I kept it within time. Thank you.
Thank you very much, Barnali. So you can unmute and ask questions.
Can I ask a question, Devendra?
Yeah, please go ahead. Yes.
Yeah, Barnali, thank you. It was a very nice presentation. Why did you choose UGMRT, I mean low frequencies? Is it better in any way?
Yes, so the good part of UG, first of all, we wanted to observe, consider a frequency range which was not explored in the past, and then we have this. We at the same time UGMRT came. At the time we started the project, and we wanted to take advantage of this wide band that UGMRT offered. So it's band 3 and band 4, which gives us a nice coverage between say around 400 to 800 megahertz. So that was the kind of frequency range which was completely unexplored, I would say, almost completely unexplored in the past. So that was the main motivation of choosing its sensitivity and wideband both.
Did you gain scientifically from exploring in that band? Just curious.
Sorry, could you repeat?
Did you gain scientifically by exploring those bands? I mean, is the emission larger there or something like that?
Yes, this is something that we didn't know beforehand. So what we found from a wideband observation is that we could obtain a wideband spectra for the first time, and it turned out that this is still a small sample, because I just said we had just observed 3 stars under this thesis project, but overall with the current amount of wideband data that we have, we find that there is a kind of peak in the right that band 3 band 4. It's kind of a splat between band 3 and band 4, and above 1 gigahertz it starts to decline, almost following a power law kind of thing. So it was completely by coincidence that it seems like the phenomena is stronger at this megahertz frequency ranges than the gigahertz frequency ranges, based on our observation of these three stars.
Thank you.
Julius, you can go ahead.
Yeah, Barnali, thank you for the nice talk. So I have 2 questions. One is that you mentioned that you need some critical condition for unstable electron distribution. So can you just outline what that condition would be, and how does star would that produce that?
Yeah, sure. So the unstable distribution I meant is that there should be a gradient positive. It's kind of a similar to population inversion, but it's kind of a classical population inversion. So there should be some velocity range in the electron distribution where there should be a more number of electrons over a larger. As we go to higher velocities. Now in this hot magnetic star, that can be produced by a magnetic mirroring, because they have this almost dipole-like magnetic field. So when it's the electrons which are accelerated somewhere here as they are going towards the star, it essentially experiences this magnetic mirroring kind of effect. And this magnetic mirroring actually removes some of the electrons, which has this very small pitch angle. They can, because they can go very close to the star. And this reflected electron population, they will have a range of velocities where there will be higher electrons at a larger velocity than the number of electrons at a smaller velocity. And that is the kind of distribution that I was talking about. This is that loss cone distribution basically.
Okay. All right. The second question is, one of the plots on the x-axis you had B magnetic field maximum divided by T effective.
Yes.
That's T stars you're plotting. So what does it physically mean by this quantity you're plotting on x-axis?
This one?
Yeah.
Yeah, so to be honest, we still that basically what we observe that with magnetic field it's kind of a linear relation, but with temperature it's kind of a parabolic relation where it first increases with temperature, then it decreases. So we have some kind of a high idea about why that should be the case, but why we still do not know why it should be around 16.5. So the increase in temperature initially is because if the star is very cool, then it will probably not have a stellar wind, and stellar wind is the source of electrons. And then again, if we go to star which has very high temperature, then probably the plasma, the magnetosphere will be too dense for the ECM to be produced. So that is we think that could be the reason behind this parabolic kind of dependence on temperature with
Yeah, so
magnetic
that is
field.
okay. The question I'm asking is like, when you take a ratio of B0 max with T effective, does it have any physical meaning, like B0 and T are related, or there are some relation in that which you anticipate, or what exactly it means? I mean, you can take
Currently,
ratio of different parameters, but taking a
yeah.
ratio of B0 with T, does it have any specific meaning?
For now, it is completely an empirical relation. Even if, in fact, don't take this. We in fact don't take this form seriously at this stage. We just said we found this two are some parameters which affects the luminosity. But what should be the exact form? We are hoping that we'll get it once we have a larger sample. Yeah.
Okay.
So.
Okay. Thanks.
Bhalchan, can we move to next talk?
Yeah, we should.
Yeah, okay. Thank you, Barnali. So next talk is by Rudrani, X-ray properties of galaxy groups and clusters. So please share your slides. Okay, please go ahead.
Hi, can you hear me?
Yes.
All right. Good afternoon, everyone. Here you can see the title of my thesis, where we have tried to understand the effect of feedback from active galactic nuclei on their surrounding environment by looking at the X-ray properties of galaxy groups and clusters. So as you know that most of the galaxies in our universe host a supermassive black holes in them, and some of these are active and they accrete material from their surrounding medium and become more massive and more luminous. These class of supermassive black holes are called active galactic nuclei. Now, due to the accretion of material onto the black hole, they release a huge amount of energy to their ambient environment. And a fraction of this radiated energy gets linked to the surrounding medium itself, and this phenomenon is called active galactic nuclei feedback. Now, it has been observed that AGN feedback has significant effect on the properties of their host galaxies as well as host dark matter halo. And one of the best ways to study the effect of AGN feedback is through the X-ray observations of galaxy clusters, because the diffuse gas inside the galaxy clusters are heated to a very high temperature due to the gravitational infall of material into the massive cluster potential. And at this very high temperature, the primary emission from galaxy cluster mainly fall in the X-ray band. So here you can see a multi-wavelength observation of a galaxy cluster, where the blue color shows the X-ray observation by Chandra telescope, which can also be seen from this top right panel. So you see here that these two regions adjacent to the black holes are free of any hot X-ray emitting gas, and they are believed to be formed by the feedback activity of the central AGN. So it has been proposed that the feedback energy from the supermassive black hole is displacing the gas from this region to an outward radius and thereby creating these X-ray cavities. So existence of such X-ray cavities inside the galaxy clusters are one of the direct observational evidence of feedback activity in these systems. So basically, by looking at the distribution of hot gas inside the galaxy clusters, we can infer more about the AGN feedback activity in these systems. So motivated by this, in our thesis, we have tried to understand this effect of AGN feedback in more detail by looking at the X-ray emission coming from the vicinity of the black hole at the galaxy groups and cluster scales, as well as by studying different scaling properties of the AGN with their host galaxies and dark matter halo. And we have carried out most of the work in our thesis using cosmological simulation, because it has certain advantages of its own over the other techniques used to study the AGN feedback phenomenon. And throughout our thesis, we have used two sets of simulation, one run by Khandai et al. 2015 and another by DiMatteo et al. 2008. Both are cosmological hydrodynamic simulation based on gauge code, and they include different various components of the universe, such as gas, dark matter, stars, and associated supernova feedback, and most importantly, supermassive black hole and feedback from them. So here in this table, you can see different parameters of both the simulation, and due to the limited spatial resolution of cosmological simulation, here the formation of stars, black holes, and their associated feedback are modeled using subgrid physics. Now, having said that, let us come to the main focus of my thesis, which can be divided into 3 parts. So where in the first part, we have studied different large-scale observables of the universe and tried to understand them in the light of feedback from the active galactic nuclei. So here I'll show you some of the key results of this part of my thesis. And let me begin with the scaling relation between the black hole and its host halo properties. And we have also studied the redshift evolution of the scaling relation by studying them at 2 different redshifts, that is at redshift 1 and redshift 0.1. And for this work, we have divided our black hole sample into 2 categories. One is central black hole and another is satellite black hole. So here in this left panel, you can see the correlation between the black hole mass with its host halo mass. And here you see that the central black hole mass is increasing with the increase of its host halo mass at both the redshifts, whereas for the satellite black hole, the mass is increasing very slightly and then gets saturated in the higher mass bin of their host halo. And we do not see any significant redshift evolution of this correlation. And here in the right panel, we see the correlation between the black hole bolometric luminosity with its host halo mass. So here also we see that the central black hole bolometric luminosity is increasing with the increase of its host halo mass, where we see a gradual decrement of the bolometric luminosity of the satellite black hole population with its host halo mass. And here also we do not see any redshift evolution of this correlation for both the central and the satellite black hole population. So basically we see a suppression of the black hole mass and the luminosity inside the massive halo, and which hint towards a deficiency of the cold gas inside the halo, as black holes primarily grow by accreting material from their surrounding environment. And one of the possible explanation of this unavailability of the cold gas inside this halo is the AGN feedback by energizing the, such as the AGN feedback is energizing the surrounding gas and evacuating them to an outward radius. And to understand this phenomenon in more detail, we have looked into the stacked density and temperature profile of the gas in the vicinity of the entire black hole population in our simulation, both in the presence and absence of AGN feedback. So this is shown here. The left and right panel shows the stacked density and temperature profile respectively, and the red dots in the blue diamond shows the scenario where AGN feedback is present and absent in the simulation in both the panels. So here we see that indeed in the presence of AGN feedback, the gas density is suppressed in the central region, and we also see an increment of the temperature of the gas in the presence of the feedback effect. So this supports our claim of AGN feedback activity in this massive halo, which lead towards a suppression of the black hole growth in the massive halo range. So after that, let us come to the second part of my thesis, where we have focused on investigating the imprint of AGN feedback from the X-ray emission of its ambient medium. And we begin by modeling X-ray emission from galaxy groups and clusters. And for that purpose, we have selected different gas properties such as temperature, density, metallicity, etc. from our cosmological simulation. And we couple them with this astrophysical plasma emission code, or APEC, in order to incorporate the detailed X-ray emission processes into a theoretical model. So here you can see the X-ray map, theoretical X-ray map surrounding black hole at redshift 1. And one thing should be noted here, that we have not considered any X-ray emission coming from this black hole itself, because it has the potential of contaminating the diffuse X-ray emission, which is of our primary interest for this work. All right, and after that we have focused to study perform synthetic X-ray observations of these systems in order to compare them with the actual observation and to test the validity of our model. And for that purpose, we need to incorporate all the instrumental response of the telescope instrumental response of the telescope into our theoretical map. And we have done that using a photon simulator called this model of X-ray response to X-rays, or MARCS. MARCS is basically a ray tracing simulator of the Chandra X-ray telescope. So here you can see the synthetic X-ray map of the same system that I showed in the previous slide. So this is 200 kilosecond synthetic Chandra X-ray map. So here you can see that all the features that are present in the theoretical map cannot be resolved from the synthetic X-ray map, and we understand these as a result of the limited angular resolution of the Chandra telescope. So basically, we see that no signatures of AGN feedback can be observed from these individual observations of these high redshift systems. So we try to stack the X-ray emission coming from all the systems in our simulation, both in the presence and absence of AGN feedback, and try to obtain a stacked X-ray surface brightness profile. So this is shown here. The left and right panel shows the stacked X-ray surface brightness profile obtained from theoretical model and mock observation. And here the magenta and cyan shows the scenario where feedback is present and absence in the simulation. So we see that presence of AGN feedback is suppressing the X-ray emission in the vicinity of the entire black hole population in our simulation. So basically in this part of our work, we have developed a machinery to perform the synthetic X-ray observation starting from the cosmological simulation data, and our results show a suppression of the X-ray flux in the X-ray emission in the presence of the AGN feedback.
Rudrani, you have 2 minutes.
Sure. Thank you. So let me come to the last part of my thesis, where we have tested the robustness of our result by comparing them with other simulation. So as you see that all the results that we have obtained so far are based on this same gadget code. So we try to understand whether the results we obtained are artifact of this particular parameters of this particular simulation, or whether they are robust. And for that, we started working with SIMBA. So this is also a cosmological hydrodynamic simulation, but the model parameters of this SIMBA are different from K15 and D08. And here you see the parameters of different runs of the SIMBA simulation. And another advantages of working with SIMBA is that it takes into account a detailed model of the black hole accretion as well as different modes of feedback from the AGN. So here you can see a result obtained using SIMBA. So this is actually the X-ray surface brightness profile for different AGN feedback modes at 2 different redshifts for the entire black hole population at these 2 redshifts. So here the red dot shows the scenario where all the modes of AGN feedback is present, and green cross shows the scenario where no feedback is present in the simulation. So here also we see that the X-ray emission is reduced in the presence of all the feedback modes, which is in accordance with our previous results obtained from K15 and D08. So we can say that our results are kind of robust. And here, one thing that we note here that different modes of feedback play important role in the suppression of the X-ray emission. So the main summary of my thesis can be stated like that. We have studied feedback from AGN, and we have seen that they impact the properties of the surrounding medium host halo as well as supermassive black hole itself. And we found a suppression of the black hole mass and bolometric luminosity. And we also see a decrease in the gas density and enhancement of their temperature, and as well as a suppression of the X-ray surface brightness profile. And we see that our results are robust by testing them for different cosmological simulation. So thank you all for listening.
Thank you very much, Rudrani. Yeah, judges, can you please go ahead?
Can I ask a question? This is Moshimi.
Yeah, please go ahead.
Thank you, Rudrani. Nice talk. I wanted to ask whether you had tested your results with other simulations like TNG 100 or TNG 50, Eagle.
No, actually, yeah, that was our future plan. So we are planning to do a comparison using the TNG simulation. So far we have not done that. We have only tested it using SIMBA.
Okay, okay, thank you.
Okay, Bhalchan.
Yeah, it was a nice talk, Rudrani. What I wanted to understand was that did you sort of try to characterize the extent to which your results would be affected by the poor resolution of the X-ray instruments by
Yes.
doing some kind of a likelihood analysis, or trying to constrain some parameters using some uninformed priors?
No, we have not done that. But here, what we have done here that, so this is the results obtained from the mock observation of the Chandra simulation. So we see that within the resolution limit of the Chandra telescope, so which is 0.5 arcsecond, so we see a difference of the statistical X-ray surface brightness profile. So we are planning to test this resolution effect for the upcoming X-ray missions like Athena and Prism using this synthetic observation technique. But we have not done this likelihood.
No. My question was very simple. That those 2 points which you see on the right plot, what's the confidence limit on those points?
Okay, we have not done that thing in our thesis.
Okay, thank you.
Okay, Indulekha.
Yeah, those last plots where you showed suppression, there seemed to be an overall shift of the curves downward. So how much is the relative amount of suppression which you see actually?
You mean here?
Yeah, both central as well as outer regions seem to be shifted downward.
Yeah, so I didn't get your question. So we are so in this plot we are probing the scale of 100 kiloparsec. So maybe if we go beyond this 100 kiloparsec region, then we can see that there should be no difference between this X-ray emission of different feedback modes. But we have not tested beyond this 100 kiloparsec radius region.
The upper and the lower are the with and the without. Is that correct?
Yes, lower is the with feedback, the upper is the without feedback, and these two other, this blue and the black shows the scenario where different other modes of feedback are included. So like this jet feedback mode or X-ray feedback mode is included. So in this black, blue and red, these all contain some kind of AGN feedback, and this green does not contain any AGN feedback in the simulation.
Okay, thank you.
Thank you, Rudrani. So let's move to next speaker, Reetika Joshi. She will be talking about study of solar jets and related flares. So can you please share your slides?
Yeah, hi.
Okay, so please go ahead.
Hi, good afternoon to all. Myself, Reetika Joshi, and I'm now a postdoc researcher in University of Oslo. So I have done my PhD on the study of solar jets and related flares under the supervision of Professor Ramesh Chandra from Kumail University, Nainital. So the topic of my thesis was solar jets and related flares. So as the sun is the most important star to give us life, and the space weather activities are making it more important. So solar jets are the ubiquitous collimated plasma ejections from the surface of the sun, from the solar photosphere to the solar corona. And these were observed with multi-wavelength analysis since 1992 or before that. So for the study of solar jets, the spectroscopic analysis of jets are important to have some conclusions from the chromosphere and transition regional lines. And the magnetic reconnection is believed to be the main triggering mechanism behind these solar jet eruptions. And according to the eruption process in the theoretical papers or theoretical studies, these jets can be classified into two classes. One is the standard and the blowout. So when we call a standard jet, so it has a narrow, less bright base. And with the blowout jet, we call them like when they form a coronal mass ejection or a breakout eruption. So the main objective of my thesis was to consider being the having the more observational stuff on the solar jets and many of the theoretical simulations and numerical experiments, still there is a debatable thing about the triggering mechanism of solar jets, that either it is the magnetic flux emergence, or it is the cancellation, or there is some helicity injection into that. Then in this regard, the main objective of my thesis was to understand the trigger mechanism of the solar jets and its relation with the solar flares, to explain the dynamics and kinematics of the solar jets, and to understand the magnetic field topology around the sun. So here it's just an example to show how the solar jets look like in different EUV and UV channels. So these are the observational data sets I have used in my thesis. So mostly I've used the space-borne data with Solar Dynamics Observatory by NASA, with the two instruments, Atmospheric Imaging Assembly AI, which observes the sun in different 7 wavelengths in EUV and UV spectral lines. And for the magnetic field data, we have used the HMI data sets from onboard the Solar Dynamics Observatory itself. We also use the stereo data set. It observes the sun from 2 different angles other than the Earth. And for the ground-based data, also we have used the H-alpha data from the 15-centimeter solar telescope at Aries, Nainital, and which is the most important and in new things is to use the newly launched IRIS interface region imaging spectrograph data set with imaging as well as spectroscopy. And to analyze the CMEs associated with the jets, we have used the LASCO data. And all the data sets in my thesis, they were analyzed with the solar software in IDEAL. So this was the first study I have done in my thesis. It was focused on the first objective of my thesis, where we have discussed about to see the relation between solar jets and related flares. So we have chosen the EUV observation from Solar Dynamics Observatory of 11 different jets, and we have found that some of the jets were also observed with Aries H-alpha telescope, and this was the motivation to choose this event, because we also have the observations available in our Aries telescope data. So when we study these EUV jets from the space-borne and the ground-based data sets, we have analyzed that there are 2 magnetic reconnection sites for the jets. We call them site 1 and site 2, and we have analyzed that there was a slipping reconnection between these two sites. For the another study of my thesis, we have started to use then the IRIS data sets with the slit jaw imaging, and for this study we don't get the spectral data, so this is done with the slit jaw imaging data. So this is to probe to know the magnetic field, to know how the magnetic field emergence is happening around the jet base. So it was done with the IRIS carbon-2 and magnesium-2 slit jaw images, and the event was at the solar limb. So it was quite clear to see that how a dome-shaped kind of structure is happening just below the solar jet, and it was quite interesting to compare it with the numerical simulation of one of our collaborators in 2D and in three-dimensional view. As we can see that our observation seems a very nice case study for the observation for their theoretical models. As we have seen, there is quite similarities between their simulations and in our observations. For a different study, we have analyzed the solar jets to see the clear relation between solar jets and the coronal mass ejections. These small scale solar jets are believed to be the main triggering mechanism for the eruption of large solar filaments, or sometimes the coronal mass ejection. So our study was focused on this solar filament, which was near to this active region, and here a jet activity happens, it pushed it down, and this big filament erupts, and it appears as the largest geomagnetic storm of solar cycle 24. And in another case study of this 2 to show the jet filament, the jet CME interaction, we have analyzed one jet from the solar disk, which erupted from the disk, and it appears as a jet-like CME in the LASCO and in stereo coronagraphs. Then further in my thesis, I have done the spectroscopic analysis of the solar jet. So it was the first study observed with the iris from 22 March 2019, that we have observed that there are the jets are from the emerging magnetic flux regions, and the nature and the dynamics of the jet reconnection sites are analyzed with iris spectra. I'll show in the next slides. So here we found that these two emerging flux regions were the main reasons to produce the solar jets. And we have found that they're very nicely covered with the iris spectroscopic slits. So why we choose this observation is interesting, that iris is an instrument, space-based instrument with some slits which are scanning the active regions. So interestingly, one of the iris slit was exactly at the reconnection point of the jet base. So we choose this to analyze it spectrally. Further, for this study, we compared our jet observations, where we have found a flux rope nearby the jet region from where the twist was transferred to the jet. So this study was done to deal with one of our objective to analyze the magnetic field at the jet base. So here we have seen that our observations were compared with the Ohm simulations of linear 2005 and 10, and we found that we have very good agreement with the simulation and the observations. So for that, we propose that a sketch or a cartoon to explain the jet ejection from a small bipole. So we propose that the reconnection occurs at a null point at a bald patch current sheet, and it converts into the null point in which form dynamically along the current sheet, and cool material trapped in between. And we have seen it in iris spectral lines as well as in this sketch. So for the further spectroscopic analysis of the jet and the jet with these iris spectral lines, we have done the similar spectroscopic analysis of the same jet, where we have seen the slit exactly at the reconnection point. So we have seen that there was a cool material inside of the hot jet, which we call a surge kind of structure. Then we have taken the different slits along the spectra, and then we perform the spectral. Okay, yeah, I'll try to finish it. So we have seen that we have done this in magnesium 2, silicon 4, and carbon 2 lines, and we have seen that there was a extra bump of in emission, which we analyzed them as the clouds are the emission of the cool material from the hot jet. Then we explain it with the multi-layer sandwich model, where we proposed a sketch that the reconnection is happening at all layers. So with this low level heating, we call them, it is confirmed with the 1600 and 1700 angstrom observations in the AIA instrument. And with the iris for the temperature around 20,000 Kelvin, the magnesium 2 and carbon 2 lines, they act as a good diagnostic to analyze the bald patch reconnection. And for the hot channels, we concluded them from the hot observations in AI, and the whole event was embedded in the corona. So for a quick thesis highlights and our future plans. So in my thesis, we have analyzed the multi-instrument analysis of the solar jets, and a different case study was done to explain, and which was quite much agreement with the magnetic flux emergence MHD models. And also we have shown the solar jets are one of the main triggering activities behind the large scale eruptions. We can compare them with solar filaments or with coronal mass ejections. And to understand the magnetic reconnection, as it was one of my objectives, so we have analyzed the iris slits, which were quite useful for in terms of the Doppler shifts, blue shift and red shift. And then we did a multi-layer sketch model to explain the different reconnection heights. So for the future work, presently I'm working with the solar physics group at Roslin Center of Solar Physics, University of Oslo, and I'm leaping forward my research with the ground-based solar Swedish telescope data, and we plan to do the spectropolarimetric with the iron-1 and calcium-2 lines, as I have used mostly the space-borne data during my thesis. So I'm planning to work with the ground-based data for the further work. Thank you.
Thank you, Reetika. Thank you very much. Yeah, so, judges, you can go ahead.
Devendra, I have a question. Devendra. So,
yeah,
Reetika, nice talk. A lot of detailed work. I mean, I understand that the basic physics theme you have is magnetic reconnection, which is working behind production of all the jets. How do you actually identify that the reconnections are taking place?
Okay, thanks, Turkesh. So for me, I see it for the magnetic reconnection that there is some magnetic flux emergence from deep of the photosphere, which is coming towards that. And it is when there is the reconnection between this emerging flux behind below and the pre-existing already pre-existing the magnetic field line. So I found that it is more from them, as you have already seen, or you know, I think about the magnetic flux emergence model, as we explained in our one of the observation, where there was a dome kind of structure. And
so I understand that, but you see all these magnetic flux emergence in the photosphere, yeah, but your jet phenomena are coronal. So how do you reconcile these two, that the same magnetic field is going from photosphere into the corona, and what signatures do you then observe in the upper heights related to magnetic reconnection, and why you call it that is due to reconnection?
Yeah, so what I think that as in one of our also in our observational study, the reconnection was, of course, we see when we see the bald patch kind of structure in the photosphere with the 1600 or 1700 angstrom data. So I feel that it is happening with the starting with the bald patch, and this this bald patch can be converted into a current sheet, and it can happen into the coronal heights or so.
Okay, thanks.
Okay, so Bhalchan, can we move to next talk?
Yes, please do go ahead.
Okay, thanks, Reetika. So next talk is by Prasanna Deshmukh. It's talking about modeling, simulation, and implementation of primary mirror control system for prototype segmented mirror. So can you please share? Yeah. Okay, Prasanna, go ahead.
Yeah, I'm audible?
Yes.
Okay. Hi, thank you for giving me this opportunity for presenting my thesis work. I'll be talking about modeling, simulation, and implementation of primary mirror control system for the prototype segmented mirror telescope. So this work was done under the supervision of Professor Padmakar at IIA Bangalore. So this is the outline of my thesis, introduction, and then we built an actuator for a PSMT telescope. This is a soft actuator. We also built the controller, closed loop controller required for controlling this actuator. Then we built a novel test equipment called as dynamic loading assembly for checking the performance of this actuator. And then in the second half, we also built a code SMT tool, which is used for simulating the primary mirror control system of an entire segmented mirror telescope. And we did several case studies, and also we implemented entire local and global control system into a network control system based control hardware. So in conclusion, the motivation for this was obvious that India is partner in 30-meter telescope, and we are giving quite significant share in this telescope from our side. And all the existing telescopes which are of 10-meter class are segmented, and TMT along with ELT are going to be segmented mirror telescopes. We wanted to get hands-on experience as well as develop some techniques and technologies required for controlling these telescopes. So that was motivation. And to move further, as we know that there is a quite good interest within the Indian astronomy community that we need a 10-meter class telescope in coming time once we have access for 30-meter class telescope. So moving towards that direction, we thought that let's build a small telescope of 1.5 meter and implement all the techniques and technologies required for such controlling such telescopes for initial prototype, and then look forward for NLOT. So that was my aim, and as a part of my thesis, I focused more on primary mirror control system, which is responsible for basically aligning the primary mirror of the telescope, which is segmented in nature, with the help of actuators and edge sensors. So edge sensors are the sensors which are planted within the gaps of the segments, whereas actuators are responsible for correcting the position of segment in terms of tip, tilt, and piston. So that was the initial idea that let's build actuator and control system required for controlling this telescope. So when we did a detailed survey, literature survey, we found that previous segmented mirror telescopes were using rigid actuators, whereas upcoming telescopes are using soft actuator due to their obvious advantages. So hence we also selected soft actuator in our design. So this is the objective of my thesis, to develop technology required for control of primary mirror of segmented mirror telescope, and especially we focused more on development of M1CS required, which comprises of local and global control system of the PSMT, and these are the sub-modules which we developed along the way in our PhD. So PSMT is a basically 7-segment test bed telescope with hexagonal mirrors of spherical profile, and overall telescope will be of 1.5 meter, and it will have active control system for correcting tip, tilt, and piston of the primary mirror, and it will be comprising of 21 actuators which are soft in nature, 24 inductive edge sensors, and will be placed on alt-azimuth mount. So this is how the architecture of PSMT's M1CS looks like, and this is basically a stack of actuators and edge sensors connected to a global control system via CAN network. So I'll give details about the actuators. So initially we derived detailed design requirement for this actuator, and these are the key requirements. One of the key requirement was a range of travel of plus minus 1.5 mm, which is quite demanding for a soft actuator considering the flexures used there. And the accuracy requirement was 25 nanometer with peak force of 23 Newton. So this was a conceptual design, and this is basically a voice coil based actuator. Voice coil is placed here, which is surrounded by a mainspring, which will take entire load. And there is a position encoder, which is nanometric optical encoder, and the entire system is supported by a offloading mechanism so as to take care of static loads which get built up due to the gravity vector. So we also did detailed modeling and found out the transfer function of this actuator by a basic modeling study, and we also simulated so as to ensure that this actuator is really viable and will work in closed loop as per our requirements. So we did the detailed simulation. This is simulation result. And after that, we fabricated this actuator at our IAA workshop. And one novel thing about this was we indigenously developed the voice coil required for this actuator, as well as we came up with disc flexure based design. I will show some details in coming slides. These were the design parameters. So for voice coil, we did detailed electromagnetic modeling, as well as we came up with the equations so as to quickly design this voice coils and get their mechanical dimensions as well as force profiles. And we actually fabricated this voice coils at our lab. And this is a calibration curve. And as you can see, the output force force constant meets the, or rather nearly meets the design requirement. And any deviation which you see here can be mitigated by closed loop operation. Further, we came up with a design of a disc flexure, which is basically responsible for giving the softness to this actuator. And we used to stack of 2 disc flexures as designed here, and to validate that it meets our range of travel requirement as well as force constant requirement, we did the FEM analysis, and these are the calibration curves, and they meet our requirement again. And as you can see, this is the calibration value, whereas design value was 0.63 Newton per mm. Again, as I said, any small deviations as observed here can be mitigated by closed loop operation. So once we have actuator, we thought of building a controller required for this. So here we use the latest PSOC based controller boards. And this is customized electronics required for giving the power to the actuator and reading the position information, which is based on the optical encoder. This is a detailed block diagram of entire actuator controller. And what we're doing here mainly is implementing a position loop so as to keep the position to the set point, tuning loop for tuning the actuator, because each and every actuator will have different slightly different mechanical properties. So to mitigate that, we do tuning for each actuator separately. Now offloading loop so as to take care of the gravity loads on the actuator. So this is the test setup at our lab. This is a basic static force test setup. We also built a dynamic test setup. In coming slides, I will show that. And we did detailed conventional tests, basically IO input-output mapping, relay tuning, closed loop step response and steady state response, closed loop position tracking and offloading. And all these tests were able to meet our requirements. Whereas what is more important is to do dynamic testing. For that, we were not having any obvious choice because we have to use, actually we have to send these actuators to the real site and test them there. So instead of that, we chose to build a dynamic loading assembly, which is a test setup, basically laboratory test setup to simulate wind-induced disturbances on the actuator. And we initially did the modeling of this also, and this also needs to be soft in nature so as to avoid any loss of force due to the friction. So those things were taken care by modeling and analysis. And this is the actually fabricated dynamic loading assembly along with one of the PSMT actuator. And here you can see the calibration curves. Basically, these are validation curves in which what we do is we collected the wind data from actual sites. We have data from Gemini South Telescope, TMT's Hawaiian site, as well as from IO Hanley. And we were able to induce those forces from top. And we were able to validate that the induced force is having same dynamics as that of the actual wind data. We found around 80% correlation, which was quite good enough. These are the actual closed loop responses. So here you can see we are introducing force on top of actuator, and actuator is maintaining its position and around the zero error. This is by kind of consuming more drive current, as you can see here, and this drive current kind of matches the profile of wind force which is exerted on top of it. So it was able to do the closed loop operation quite well with 12 nanometer RMS tracking error, whereas our requirement was 25 nanometer. And here our wind speed is 4 meter per second. And since PSMT is planned for Hanley site, we modulated the wind profile so as to meet Hanley's. Yes, sir. Yes, sir. So this is the force track requirement wherein we were able to achieve a constant force disturbance on top of the actuator with 5 nanometer error. So further, I'll give a brief about the Code SMT tool which we developed. It is basically taking the edge sensor information, processing it, and controlling the actuators. But since there is no one-to-one mapping between the actuators and sensors, we require least square fitting. But for this, we use a SVD-based algorithm. These are the equations. I'll not go in details of this, whereas I'll show you one tool which we developed, which is capable of having these features, wherein we can do parametric sensitivity analysis so as to see which parameter is more sensitive for a given segmented mirror telescope. And since there are so many important parameters, it is why it is good to initially simulate and find out and rather constrain important parameters. So these are the ones: size of the segment, actuator position, and then sensor position, sensor type, and number of rings in the telescope. And then we have a lot of other features, including PSF simulation and image motion studies. So this tool is capable of having standard flavors of PSMT, NLOT, Keck telescope, SALT telescope, and TMT as well, up to 12 rings. And we can simulate the dynamics of any segmented mirror telescope in this with our custom parameters. This is a sample result where you can see the actuator edge sensor state as well as the mirror shape and its corresponding PSF shape. And here you can see with one iteration, we were able to achieve from 85 nanometer to 30 nanometer correction in the image PSF. Further, we have done 2 case studies, which I will not go in detail, but these case studies are basically to see effect of wind and vibration on top of the entire telescope. This is called as active control simulation study. And another study we have done is error multiplier analysis, wherein segmented mirror telescopes are prone to something called as focus mode effect, and that effect can be avoided, but we can mitigate its effect or reduce its effect by doing parametric sensitivity analysis. By doing this error multiplier study, which can be done by using code SMT tool. So finally, we have implemented yes, sir. So
Yeah,
finally, we have implemented entire local and global control system in real hardware, where we have 21 local controllers, a global controller which is connected via CAN network. And we were able to demonstrate that this meets our requirement of PSMT's different modes of operation as identified here. And these are the typical modes of operation for a given segmented mirror telescope. These are the test results to validate it meets open loop and closed loop requirements for single and multiple actuators. And yeah, in conclusion, we initially aim to model, simulate, and implement primary mirror control system for PSMT. We were able to develop different technologies like soft actuator, its controller, test equipment called as DLA, as well as a code SMT tool, which is a generic tool for simulating segmented mirror telescopes. And in coming time, we plan to utilize these hardwares and softwares for PSMT and analytic telescope. These are the publications. Thank you.
Thank you, Prasanna. Thank you very much. Okay, so judges, please go ahead.
Yeah, Prasanna, that's a very interesting talk and clearly quite a lot of work. I had a few questions, but I'll just restrict myself to a couple. So did you try simulations or actual implementation of robust control algorithms in in trying to achieve that 10 nanometers in the presence of wind and vibration disturbances?
Yes, sir. Yes, sir. So we actually we were able to simulate it. We didn't use it in the reality because by doing relay tuning, we were able to achieve required desired performance.
No, my question is that these are still conventional control criteria, you know, proportional and integral gains and so on. You can have much better quantitative feedback techniques to do these closed loop controls. So did you explore that?
Yes, yes. We just explored in terms of simulations, as you can see here.
Okay.
We were able to simulate robustness.
That's fine. The last question I wanted to ask was that this actuator and the electronics design, is it possible to sort of convert it to a space payload where the weight, volume, and the power, all three of them are at premium? So
yes, we had to use some smart designs. For example, for the flexures, we use a very thin flexure, whereas the conventional design asks for using pivoted flexures, which are quite heavy and bulky. But definitely, all these techniques used here can be implemented for space by reducing the volume as well as mass. That is very much possible. Miniaturization is very much possible.
Okay, thank you.
Okay, thank you, Prasanna. So let us move to next talk by Archita Rai, CJ. Okay, she will be talking about infrared astronomical instrumentation and polarization studies.
Good afternoon, everyone. So today I'll be presenting the work which I have done during my thesis. So the topic of the thesis is infrared astronomical instrumentation and polarization studies, and it was done under the supervision of Dr. Sashikiran Ganesh at Physical Research Laboratory. So the thesis, just a second. The thesis embodies two separate works. So the first work, which is a small segment of it, is the scientific polarization study and analysis of stars in the molecular clouds and look for the interstellar polarization contribution. And the second part, which is the major part of the thesis, is the design of an multi-mode near-IR instrument, which we call as NISP, as abbreviated for Near-Infrared Imager Spectrograph Polarimeter, to enable observations with precision on PRL's new 2.5 meter telescope. So this is a completely indigenous in-house built instrument. So discussing firstly about the first, this is not moving. It's the cursor is not moving.
Yeah, we can see your cursor. Maybe you can just try to click and then see if it moves now.
So discussing first about the scientific part, which is relating to the interstellar polarization observations with next pole. So the main concept which one needs to put in mind is, what do we mean by ISM polarization? So the ISM polarization means that when you have a unpolarized light which is traversing the interstellar medium, which consists of dust, asymmetric dust particles, then in the presence of magnetic field, these dust particles are getting aligned, and because the starlight which is traversing through this medium is getting differentially absorbed by these dust particles, and whatever light we are viewing is actually polarized. So with this concept behind, if we go for the mode of operation and the observations we have done, so you can see here that there's a wire grid polarizer module which has been attached to the existing NIX instrument. There's a NIX instrument, near infrared camera spectrograph at PRL, and this is a very small section where we used to place the beam splitter. So we thought of utilizing it to place a wire grid module on a rotating shaft and then utilize this for polarimetric observations. And because the rotating shaft was motorized, so we could get the images at different angles. So we took the angles at 0 degree, 45 degree, 90 and 135. And then with the help of Stokes calculation, we could get the polarization parameters estimated. So here are the few of the main results which we received from this observation. So this is a polarization vector map, and this I'm showing for only H-band imaging, what we have done. So for the H-band polarization, what we received, I have overplotted it on the 2-mass image of H-band, and here we can, the main thing to see is that all the polarization vectors are very nicely aligned with the galactic magnetic field, and the overall orientation in a way is following the interstellar polarization. And the other thing which we wanted to estimate was the magnetic field strength of the RNO cloud clump, which is embedded within the L1340 cloud, which is the work here. So with the help of the Chandrasekhar Fermi method, where your mean magnetic field strength, the mean field, depends upon the local density, the line of sight velocity, and the dispersion in the position angle of polarization. So the dispersion of the position angle polarization was seen to be very less, which shows that there is a significant magnetic field which is present there, and with the numbers which we see, we could estimate a 42 microbars magnetic field for this particular region. So that was about the first segment of the work which we had done. Now, because we have these scientific observations, and they need more better and better instruments to enable their measurements. So with this, the previous work, we could gain a lot of experience about what we want in the instruments which we are building. We want better precision, efficiency, and avoid the sky variations which happen in near infrared basically. So in adding these new facilities to the existing ones, we proposed to build the NISP instrument, which includes a dual beam polarimeter, that is a wedge double volaston, in short form for WDOVO, in the near IR wavelength band, apart from imaging and spectroscopic modes. So this was one of the first near IR polarimeter in India with observations in 4 simultaneous beams. So the further slides will tell what we mean by this. So this is the design specifications for the NISP instrument. So the main thing is that the telescope primary size we have is 2.5 meter, and the field of view requirement as per the scientific works we want is 10 arc minute by 10 arc minute and imaging mode. Then the filters we are going for near IR are YGH, K-short and K, and we also have provision for narrowband filters. The spectral resolution requirement was around intermediate for 2000 resolution, and the polarimetry is single shot. getting all the 4 images. So with this, moving on to the imaging design. So this is the imaging design of the NISP instrument. Behind this Cassegrain focus, we have the entire telescope optics and the cryostat window. This imaging layout only showcases the instrument part of the design which I have done. So here we have the collimator optics till this lens. Then we have the filter wheel setup near the pupil plane area, and then we have the camera optics. So these are all the materials which have been utilized for the making of this optical design, and all these materials have been chosen with their efficiency in the infrared and the at cryo temperatures. So this was the spot performance which we received with the imaging design. So here on the right hand side, it shows for the entire band from 0.9 to 2.5 micron, which the instrument is entitled for. But on the left side, I'm just showing for one of the wavelength band, the complete H band. So we can see that the performance is actually diffraction limited, what we are achieving from the design, because since it is a ground-based instrument, so whatever we want is a scene limited performance, but 1 pixel around 18 micron, we want around less than 54. If we do 3 pixel sampling, then we want around less than 3 pixels, whatever images we get. So here we are getting close to diffraction limited. So this is good as per the design is concerned. Then the polarization design comes into picture. So for the polarization mode to work, we have to place another component in the filter wheel part. So this was the filter wheel part, and here this component is the wedge double volaston. So the design of the wedge double volaston was made, and this with the placement of this, we will get 4 simultaneous beams which can be seen at the detector plane. So how does this work actually? For the usage of a wedge double volaston, the input field, which is coming from the focal plane mask, which has to be placed at the Cassegrain focal plane, that focal plane mask is giving us an input field which is incident on 2 of the volastons. One is volaston down and the other is volaston up. So both of these volastons, once the input field is incident on it, these volastons, as per their definition, they are also going to divide these beams into extraordinary and ordinary beams. And because of that, you are getting 2 orthogonal components from each of the volastons. Now, if these volastons are at 45 degrees to each other, then what we will be getting is 090 from one of the volastons and 45, 135 from the other. So using this concept in a single shot, you are getting 4 images. So this is the wedge double. If we just focus on the detector plane, so using this wedge double volaston, these are the 4 horizontal strips which we will be receiving, and each of these strips are non-overlapping. That has been taken care in the design of the wedge double volaston. All the angles and the material we are choosing, everything has been chosen, and then the custom design of this particular component has been made so that we can get non-overlapping beams at the detector plane. So these are the non-overlapping beams, and this is how the orientation will look like. So we have 0, 90 degree and 45, 135 degree as per these strips. And each of these strips is of 1.4 arc minute by 10 arc minute. So since the imaging field of view was 10 arc minute by 10 arc minute, here to have a complete non-overlapping amongst each of these separate 2 minutes. Okay. Each of the separate strips, we had to cut down on the horizontal part, and that is why it is coming as 1.4. And these are the spot diagrams from polarization. So because one of the important thing which has to be taken care of is the lateral chromatism, which we can see for these multiple wavelengths. So using the material YLF, which we are using for our case, we could cut down on the lateral chromatism part too. So the third part is the spectroscopic design. So a grism has been utilized for enabling the spectroscopic mode. Now, why a grism we chose was because the design which I showed was a straight design, and the grism is the only component which can give us an undeviated beam and hence be placed in a multi-mode instrument, so that there is no bending of rays required for the dispersions. So this is the design. Here you can see that in the second filter wheel, the grism has been placed, and the separate all the separate wavelength bands had been shown for the Y band, J band, H band, K short, and K, and the dispersion as can be seen on the detector plane. So this is how it was covered. So with this, I summarize the work. So the optical design of a near-infrared instrument with multiple modes was done, and the components and everything was under discussion with the vendors. The various science cases which require very focused imaging, intermediate spectroscopy, and precise polarimetry will benefit. And we also had the infrared polarization study of a dark cloud, LENS 1340, done to understand the near-IR polarimetry and hence get an insight into the geometry of dust and magnetic field. And these are the publications. And so since the world is evolving with bigger and better telescopes, so we want bigger instruments. So that's all. Thank you.
Thank you very much. So, okay, so judges, you can go ahead.
Yeah, Archita, so nice talk. I have two questions. One is like, how big is your team and what is your exact contribution into this, or everything is shown by you? Or
Yes, so basically we have a team consisting of the optical design, then the mechanical part and the electronics. The optical design entire part has been done by me, sir. So,
and analysis as well?
What?
Optical design and analysis as well?
Yes, sir. The optical design and analysis for it.
Okay. Now, could you just go back to your very first spot diagram? Yeah, that one. So in the left image, you have this, the three are quite circular and the middle and the bottom right, they're rings. So what are those differences and why those rings are coming up?
These two you're talking about?
Yeah, correct.
Actually, these are for the extreme field. So what we have done here is, like, you can see that it's total of 8 circles. So 4 are for the positive side of the your optical layout, your optical beam, and 4 are for the negative side. So these 2 fields are for, like, if you are seeing like 10 arc minute, then for positive 5 arc minute, this is the spot diagram what you are getting, and this for the negative 5 arc minute. So since it is within diffraction limited, these spots this shape doesn't matter, because whatever you will be getting will be seen limited. So it will be
that is correct. So
yes.
the shape doesn't matter, but I'm just interested in that.
Yes. So
why these shapes are coming.
Yes, so this happens actually because in the in this one also, if you can see that for the extreme fields, usually other distortions come into picture, like coma or astigmatism. So because of that, it tends to get a bit distorted up as you are moving away from the main beam path.
Okay, and which one is for the main beam path here in
the first one, this one, and then this one.
Okay.
So the first 4 are for positive side, and then the next ones are for the negative side.
Okay. Okay, thanks.
Okay, so thank you, Archita. So let's move to the next talk by Apurba Bera. She will, I think, talking about the evolution of neutral atomic gas and star formation.
Hi, am I audible to you?
Yeah, let's go ahead.
Okay. I hope my screen is visible to all of you.
Yes.
Okay. So I'm Apurba Bera. I did my PhD on the evolution of neutral atomic gas in star-forming galaxies with Jairam Changalut at NCRT IFR. So my talk will have these few elements. I'll start with an introduction to neutral gas in star-forming galaxies. Then I'll move to an H1 21 centimeter stacking analysis at intermediate redshifts that we did to measure the average H1 properties of galaxies at redshift of 0.35 and the H1 scaling relations at the same redshift. Then we used these measurements to infer the cosmic H1 density and H1 mass function at redshift of 0.35. And finally, we used all these measurements to understand how the low redshift evolution of neutral gas reservoir in galaxies take place. Then I'll finish with the key results and summary. So it is known that the star-forming galaxies evolve through their lifetime. It is also known that most of the star-forming galaxies are found on something called a main sequence, which is an almost linear relationship between their star formation rates and stellar mass. Now, talking about the evolution of star-forming galaxies, it is also known that the main sequence relation itself shifts downwards at lower redshifts. That means galaxies at the same stellar mass at higher redshifts are more star-forming compared to similar galaxies at lower redshifts. It has been also known for a while that the cosmic density of star formation rate varies strongly with redshift. It starts increasing from about redshift of 8 towards lower redshifts, peaks around redshift of 2, and then drops by about a factor of 10 at the present day universe. However, we want to understand what happens to the neutral gas in these star-forming galaxies, because the neutral gas dominates the total mass of the interstellar medium of these galaxies, and also it provides the raw material for star formation. We know that neutral gas has two components, the atomic gas and the molecular gas. The atomic gas is the primary fuel reservoir for star formation, which cools down to form molecular gas clouds. And then the molecular gas clouds collapse under their own gravity to form stars. The neutral atomic gas only has indirect influence on the star formation process as far as we know. The evolution of the neutral atomic gas properties of galaxies is not yet well understood. And it is also not understood how it is related to the evolution of the star formation properties of galaxies. The atomic gas reservoir has two primary constituents, atomic hydrogen, which is more than 60% of its mass, and atomic helium. The atomic gas reservoir is a dynamic entity. It gets depleted in star formation process and also gets depleted by outflows driven by star formation or the AGN feedback or RAM pressure stripping if the galaxy is in cluster environments. And the gas reservoir also is sometimes replenished through accretion of fresh gas from the circumgalactic medium and the intergalactic medium, and also by the merger events. It is also known in the local universe that the atomic gas properties of star-forming galaxies are well correlated with their other properties like stellar mass, optical magnitude, where the correlation is tightest for the B-band magnitude, and the optical or UV colors. However, because we don't have much information of the atomic gas properties of high redshift galaxies, we don't yet know how these scaling relations evolve with redshift. The evolution of these scaling relations is important to understand because it gives us the idea of how atomic gas reservoir of galaxies evolve with redshift and how it is influencing star formation. Detecting the H1 21 centimeter emission of distant galaxies is a difficult job. The H1 21 centimeter emission is the best probe of atomic hydrogen in galaxies because it's hyperfine transition. It's intrinsically weak and requires very deep observation to detect this line from galaxies at redshift, let's say, at higher than 0.2. However, the method of stacking the H1 21 centimeter signal from different galaxies, or let's say number of galaxies in a sample, gives us the idea of the average properties of the galaxies of that population. Although this does not give us any information about the individual galaxies, this can still be used to understand the average properties of the sample and to measure the H1 scaling relations at high redshifts. Previously, stacking experiments have been tried at intermediate redshifts, that is redshift between 0.2 and 0.4. However, they yielded low significance detection of the average H1 21 centimeter emission and led to large uncertainties on the measured average H1 properties. So we started an H121 centimeter survey with the UGMRT, which has a band 5 receiver of 400 megahertz instantaneous bandwidth, which covers the H1 line from the local universe to redshift of 0.4 in a single setup. Our survey had two primary goals: to measure the average H1 properties of star-forming galaxies at intermediate redshifts and use these measurements to probe the evolution of the atomic gas reservoir of star-forming galaxies. So we chose the field extended dot strip known as EGS for our survey, which is shown in this image, where the coverage from other surveys, other optical, infrared, and UV surveys are shown in colors. And this circle here shows the GMRT pointing we chose for our survey. The total allocated time was 347 hours in 4 cycles, which yielded about 250 hours of on-source time. So here I'm showing the stacked H1 21 centimeter signal from the blue galaxies, which are believed to be the star-forming galaxies at redshift of 0.20 to 0.42. So the left-hand side shows the average H1 21 centimeter spectrum of the sample, and the right-hand side shows the image, the H1 emission image of the sample of the same galaxies. And here the 3 images show the individual channels within the FWHM of the line at a resolution of 30 kilo/second, which shows that the stacked emission is very clearly detected at a significance of about 8 sigma. So we moved on to dividing the sample in bins of different properties, starting with MB, to find out the H1 scaling relations with these properties at redshift of at a median redshift of 0.35. The solid blue line here is showing the MH1 MB scaling relation for blue star forming galaxies at redshift of 0.35, and the dashed dotted line here, which is a steeper slope, shows the same relation at the local universe. You can see that the relation appears to have evolved significantly from redshift of 0.35 to the local universe, and the relation at redshift of 0.35 is significantly flatter than the same in the local universe, which indicates that faint galaxies at higher redshifts are more gas rich compared to similar galaxies at lower redshift. We used this relation and the average H1 mass to measure the cosmic H1 density at redshift of 0.35, which is shown as a star here. And this shows, along with the other available measurements in the literature, that the cosmic H1 density is actually practically constant from redshift of 0 to about redshift of 1, and only starts evolving at redshifts higher than that. And using the same scaling relation and the B-band luminosity function at redshift of 0.35, we inferred the H1 mass function, which is the distribution of H1 masses of all star-forming galaxies at redshift of 0.35, which is shown as a solid blue line here, and the shaded region is its error bar. And the local relation is shown here.
Apurba, you have 2 minutes.
Yeah, which is clearly different from the relation at 0.35. And this shows that galaxies with high H1 masses are rarer and redshift of 0.35 than they are today. We also measured the MH1 M star scaling relation, which is with scaling relation with the stellar mass. And it turns out that this scaling relation is approximately the same with the same scaling relation at the local universe. And we also measured the H1 depletion timescale using that same scaling relation with stellar mass. The results are shown in blue points and straight line. And the similar depletion timescales at the local universe are plotted here. The median values are these red squares. The massive galaxies, which are about more than 10 to the power 10 solar mass or so, are clearly have a lower gas depletion timescale, that is higher star formation efficiency at high redshift compared to the local universe. Now we used this MH1 star scaling relation, the main sequence relation, and the scaling relation from the molecular gas to probe the evolution of the neutral gas reservoir in galaxies from redshift of 0.35 to the present day universe. So this blue dashed line here shows the evolution in the atomic gas reservoir in star-forming galaxies as a function of their present-day stellar mass. It turns out that most star-forming galaxies have kind of maintained their atomic and also molecular gas reservoir at the same level, although their stellar masses have increased by a significant amount, between 80% and 30%. That says that significant infall of neutral gas has happened on the star-forming galaxies over the past 4 gigayears, which is from redshift of 0.35 to the present universe. We can also quantify that number, what is the rate of neutral gas infall in the past 4 gigayears, which is the total gas that has fallen in divided by 4 gigayears, which is shown as again a function of their present-day stellar mass in a blue solid line. And the dashed line shows the average star formation rate of the same galaxies in the same time period. It turns out that the time average neutral gas infall rate is approximately same as the time average star formation rate, which is a remarkably new result. And the infall rate is broadly consistent with the predictions of the semi-analytical models and the numerical simulations.
So please wind up now.
Yeah. So with that, I'll wrap it up and just summarize with the key results. The key results of my from my thesis are these: the MH1-MD scaling relation is flatter at redshift of 0.35 compared to the local universe, while the MH1-M star scaling relation agree within the error bars. The massive galaxies appear to have shorter H1 depletion timescales at higher redshifts. The cosmic H1 density does not seem to evolve from redshift of 0.35 to redshift of 0. The H1 mass function, however, appears to be different at redshift of 0.35, with far fewer galaxies with high H1 masses. The galaxies appear to have maintained their atomic gas reservoir in the past 4 gigayears, which indicates that they have accumulated significant amount of neutral gas through accretion or gas infall. Thank you.
Thank you very much, Apurba. Okay, so judges, please go ahead.
Shall I ask a question?
Yeah, please go ahead.
You mentioned here that neutral gas infall has caused the increase. So is it due to gas accretion or gas mergers? Can you give any comment on that?
So the current measurements do not distinguish between whether the infall happened through mergers or accretion. But because merger events are discrete and are relatively rare, I would guess that most of the infall happened through accretion from the CGM, basically.
Okay, so is there some model for that? Do you know?
There are semi-analytic models. Yeah, you can go through this paper by Korea in 2018, who kind of model this gas infall from the circumgalactic medium to the disks of the galaxies.
Okay. Okay, thank you. Can I ask one more question?
Let's go to Indulekha first.
Okay.
I just wanted to know whether you could separate these into field galaxies and cluster galaxies. Or...
Yeah, we in principle can, but the current signal to noise ratio is still not good enough that we can measure the scaling relations independently for field galaxies and cluster galaxies. But that is a future plan. So we are doing surveys on other fields as well, where we believe that we will have sufficient signal to noise ratio to find out the effect of environment.
Thank you.
Yeah, Mosmi, you have a quick question.
Yeah, actually, if you stack the H1 spectra, you will also get, or if you look at individual spectra at different redshift, evolution of velocity dispersion can also be obtained. Have you done that?
So in principle, that can be done if you have a very large sample. But see, this sample is about 500 galaxies right now. And the galaxies are oriented in different directions. That has an effect on the observed line width. And also the galaxies are between MB of -16 and -21, which is a large range. So the line widths are different for different galaxies. and now there is a convolution with the orientation. So now with only 500 galaxies, it's very difficult to say something about the line width actually.
Okay.
Of course, if you have several thousands of galaxies, you can do that, and you can in principle find out the evolution of the Talley-Fisher relation, which is one of our future goal to actually probe the dark matter halo and all. But yeah, the current signal to noise ratio is not good enough.
Okay, thank you.
Okay, so Prerna, maybe you can send your question on chat box, so Apurva will reply. So we have to move on. So thank you, Apurva. Now let's go to the next talk by Bhoomika Rajput about the optical-GeV connection in Fermi Blazars.
Good afternoon, everyone. I'm Bhoomika Rajput, and today I will be presenting my thesis work with the title "The Optical-GeV Connection in Fermi Blazars." I've done my thesis work under the supervision of Professor C.S. Talley at IIM Bangalore. So I will start with a brief introduction of blazars. Blazars are a most special class of AGN, and they are the most luminous source in the universe. These are the compact radio sources and mainly hosted by elliptical galaxies. Blazars belong to jetted class of AGN, and they emit relativistic jet which are pointed close to our line of sight. And that's why they show flux variation over the entire electromagnetic spectrum, that is from radio to gamma rays. And they are also highly variable in optical polarization. And FSRQ and BLX are the two classes of blazars, where the FSRQ show equivalent width greater than 5 Armstrong in their optical spectra, and BLX show equivalent width less than 5 Armstrong in their optical spectra. Now coming to the spectral and energy distribution of blazars, the two main components are there in the SED of blazars, the low energy component and the high energy component. Low energy component covers from radio to UV or X-rays, which is mainly produced by the electron synchrotron emission process. The high energy component covers the energy range from X-ray to TeV gamma rays, and which are mainly produced by inverse Compton or hadronic scenario. So I'm showing here the SED of FSRQ source 3C279, which is here it is the low energy component, and this one is the high energy component. And this is the SED of BLX source Mercurian 421. This is the low energy component, and this one is the high energy component. Now the source of energy emission in blazars. Mainly two models are defined to describe the energy emission in blazars. The low energy emission, which is mainly comes from the synchrotron emission process of the relativistic electrons. The high energy emission comes from the inverse Compton process. And inverse Compton process is further divided into two parts, which are the synchrotron self-Compton, where the seed photons are the same photons which are produced through the synchrotron emission process. And this process is mainly dominated in the BLX sources. Other one is the external Compton process, where the seed photon take part from the outer part of the jet, which are the mainly accretion disk, BLR or dusty torus. And this process is mainly dominated in the FSRQ source. And in the hadronic model, the low energy emission is mainly produced same as the electronic model, where the low relativistic electron produce low energy emission through synchrotron emission process, but the high energy emission comes through the synchrotron process of the relativistic protons. So till now, the high energy emission in the broadband SED of blazar is not clear yet and still in debate. So our motivation is to find out that what is the cause of high energy emission in blazars, whether leptonic scenario or hadronic scenario. Or we want to check whether one John leptonic model can explain the broadband SED of blazars. So we have the two possible approaches. So we through them we can check these scenarios. First one is the via SED modeling. This is a difficult approach because we need data over multiple wavebands plus a good theoretical model. The other way to study this scenario is that we can study the correlation between optical and gamma ray flux variation. This is an easy approach. In what happened in this second approach, that in leptonic scenario, the low energy optical and high energy gamma ray should be correlated because the same relativistic electrons are responsible for the emission of low energy as well as high energy. But in hadronic scenario, the optical and gamma should not be correlated because optical is coming through electrons in proton, where the gamma ray is coming from the protons in proton. So what is our approach? That we have to generate the long-term gamma ray light curve using Fermi data, and we look for the correlated optical and gamma ray flux variation. So these are the list of sources which we chose for the study of optical and gamma ray flux variation. These 5 are the FSRQ sources: 3C454.3, PKS 1510-089, 3C279, CT102, and 3C273. Other 3 are BLX sources, which are the Oj287, AO0235 plus 164, and PKS 2155-304. So what we have, I'm showing the example of one source. This is the PKS 1510-089. We have generated the multi-wavelength light curve of this source over the period of 10 years. In first panel, we are showing the one-day wind gamma ray light curve, which is generated using Fermi data. In second panel, the X-ray light curve, which is generated using Swift XRT data. The third one is optical V-band light curve, which is taken from Stewart V-band and Smart's V-band. And the fourth one is the IR light curve in the J and K band, which is taken from Smart's data. And the last one is polarization light curve, which is taken from Stewart. So but we have generated this multi-wavelength light curve for all the 8 sources, and we look for the optical or gamma ray flare and their corresponding flare, whether it is present or not. And we have also looked for the quiescent state, where all bands are in quiescent state. So I'm showing here the zoomed version of first epoch. This is 20-day period where in first panel gamma ray flare is present, but in third panel the optical flare is not there. And we generated the multiband SED using one zone leptonic model. This green line is showing the synchrotron part. The cyan line is presenting the accretion disk component. And this one, yellow line is the synchrotron self-Compton, and red line is for the external Compton. So what we found in this study for our 8 sources, we found that 3 cases. We found correlated optical and gamma ray flares. The second one, that optical flare is there but without gamma ray counterpart, and that can be due to change in magnetic field, because synchrotron emission is dependent on magnetic field, but inverse Compton is independent of the magnetic field. The third one is gamma ray flare without optical counterpart, which can be due to change in the bulk Lorentz factor. Now, in the 5 FSRQ sources, in 3 sources, PKS 1510-089, CT102, and 3C273, we found that optical emission is mainly dominated by the accretion disk. In other 2 sources, 3C279 and 3C454.3, we found that optical emission is mainly dominated by the jet synchrotron emission process. And in 3 BLX sources, out of 3 BLX sources in AO0235 and Oj287, the high energy gamma ray is mainly coming because of external Compton. And in one source, PKS 2155, we found that gamma ray is mainly responsible because of synchrotron self-Compton. Okay. The second part is with the optical-GeV connection, we also look for the long-term gamma ray variability, flux variability. We took all the 1,000 sources from the Fermi 3FGL catalog, where the 639 are BLA and 481 are FSRQ. And we divided our sample into the low synchrotron peak, high synchrotron peak, and intermediate synchrotron peak Blazer. And we generated monthly wind gamma ray light curve for the periods of for the period from 2008 to 2017. So this is the light curve, some sample light curve of BLX sources, and this is the flux variability amplitude distribution. This panel shows the BLX for BLX sources, and this is for FSRQ sources, and this is the cumulative distribution for these 2 sources, which shows that these are 2 different distributions. And this is the variability time scale distribution. This one is for FSRQ. This is for BLA. And this is the cumulative distribution. And in this, we found that more than 50% Blazars are variable. FSRQs are more variable than BLX sources. And in the sample of LSP, ISP, and HSP sources, low synchrotron peaked are most variable object. And FSRQ showed the duty cycle of variability around 66%. And for BLX, the duty cycle of variability is 36%. Now, the last part is the study of correlation between optical flux and polarization, because we know that the low energy emission is well defined from the electron synchrotron emission process. So there should be a correlation between optical flux and polarization. So we selected 19 sources from Steward observatory data to study the correlation between optical flux and polarization, where the data is available for the 10 years or more than 10 years in the optical viewband. And we have selected 19 sources, where 8 sources are FSRQ and 11 are BLX sources. And we also generated one-day wind gamma ray light curve of these sources. And we look for the correlation between optical flux and polarization on short term as well as on long-term time scale. So this is the one case of FSRQ source 3C454.3. This is the one-day wind gamma ray light curve. This is the optical V-band light curve. And this one is the polarization. The blue shaded region are the correlated or anti-correlated epochs on long-term time scales, and the orange one is showing the correlation or anti-correlation between optical flux and polarization on short-term time scale. Yeah. So on long-term time scale, we found that we found total 79 cycles, wherein 34 we found positive correlation, and in 3 we found negative correlation. On short-term time scale, we found total 55 epochs, wherein 47 we found positive correlation, and in 8 we found negative correlation. And this different correlation, we found that because of multiple emission regions are present in the jet of Blazars. So coming to the overall conclusion, we find that different varied correlation we noticed between optical and gamma ray flux variation, but these all are explainable by one-zone electronic model. And FSRQs are more variable than BLX sources. And in the study of optical flux and polarization correlation, we also found different varied correlated behavior between these two. So our first start, where we wanted to study the optical and gamma ray flux variation, this cannot be able to constrain the leptonic versus hadronic scenario in the emission model of Blazar jets. And these are the publications. Thank you.
Thank you very much. Yes, so judges, you can go ahead.
Yeah, Bhoomika, interesting talk. One of the sources which you mentioned, the flaring mechanism is one proposal for the flaring mechanism is a binary black hole, that is the Ojha 287. So what do you see in the case of Ojha 287? Because it may not be, the correlation in flares may not be related
No, in Ojha 287 we found, because it is BLX source, we found optical and gamma ray flux correlated, and the high energy part is explained by the external component. I mean, these two are correlated in Ojha 287, optical and gamma ray flux variation.
Yeah, I guess my point was that there may be other possible explanations which may complicate the story.
Yes.
So have you considered some of those things already? It's a fairly complicated field. So I was just...
We have not considered that. Only the emission is coming because of the jet scenario.
Okay, thank you.
Okay, any other question, judges?
Yeah, I have one question. Bhoomika, in the very first slide or second, when you were saying that SED distribution and you need a good theoretical model.
Yeah.
What theoretical model are these? And yeah, the first one here, via SED modeling, the possible approaches. And how do you define the goodness of a theoretical model?
No, because goodness of theoretical model, here we are considering only one zone. It can be two-zone electronic model, and whether it can be time dependent or time independent. And now neutrinos are also discovered. So it is like possible that hadronic model is also a favorable approach to define the broadband density in context of Blazars. So, I mean, yeah.
So a theoretical model is essentially which, I mean, I have no idea about these, but when you look for a theoretical model,
yeah,
what kind of modeling are these? There is spectral modeling, or there's some sort of simulations, or what's happening in those models?
No, only
example
simulation. Just we are taking the different mechanisms, synchrotron and self-synchrotron and inverse Compton. So using this mechanism process, we have modeled our data, observation data. So it's
okay.
Okay, thanks, Bhoomika. So let's move to the last talk of this session by Prerna Rana, Relativistic Dynamics in Black Hole System and Implication for Observations.
Am I audible? Thank you very much for giving me this opportunity. Myself, Prerna. I'm a postdoctoral fellow at TFR Mumbai, where I'm working with the NPTA collaboration. I did my PhD at IIA Bangalore, and my thesis supervisor is Professor Arun Mangalam. This is the outline of my talk. I'll first motivate the work I've done in my thesis, and then I'll discuss 3 projects which are part of my thesis, and finally I'll conclude my work. So we know that in universe we have various categories of black holes categorized based on their masses, and if we look at the X-ray light curves of these black holes, we'll see the variability of X-ray light curve is a few hours to days for supermassive black holes, and few seconds for intermediate, and milliseconds for stellar mass black hole in X-ray binary. And if you compare them with the theoretical frequency, which is the frequency of oscillation, which is basically azimuthal frequency at in a more stable circular orbit, we'll find that it's very, very comparable to the observed variability seen in the X-ray light curve. So this is the motivation of my thesis, that the frequency of oscillation of matter, which is basically the frequency of oscillation of trajectories around a black hole, is important to explain this observed variability in astrophysical systems. So what are these, how these trajectories look like around a rotating black hole? That's what I show here. So these are 3D trajectories around a Kerr black hole, where Kerr black hole is a rotating black hole in general relativity. So on your left side, you see a non-equatorial eccentric orbit, and in the middle, you see a spherical orbit with constant radius. And on the right side, you see a special orbit, which is a separatrix orbit, which is basically a separation between bound and unbound. So in the first project of my thesis, we have analytically derived the equation of motion for all these kind of trajectory around the Kerr black hole. So this is, I'm just giving an overview of my thesis. First, we develop an analytic framework using general relativity in Kerr spacetime, and we study bound orbits in various parameter space. We study non-equatorial eccentric orbits, spherical and separatrix, etc. We find the fundamental frequency of oscillation of these trajectories, and then we use these fundamental frequencies to develop models for X-ray observations. So on your left-hand side, at the bottom is a model that we developed, which is generalized relativistic precession model, which is a model for QPO frequencies of X-ray light curve in X-ray binaries, and we have also implemented this model to QPOs in AGN. On the right-hand side at the bottom is another model, which is a relativistic orbit model to explain Fourier power spectral density shape in AGN. And there's some ongoing work also to understand the periodic orbits and to quantify them in the parameter space. And also there are various applications of the analytic result that we have. And this work is already nicely cited. So this is the first part, which is the main part of my thesis, which is publishing classical and quantum gravity. So if you look at Kerr spacetime, it's a spacetime of a rotating black hole characterized by spin of the black hole, which is A, and mass of the black hole, which is m dot. So if you look at these equations, which are very complicated, which was derived by Carter in 1968, these are having this radial and theta components, and the radial component has this function r minus r1, r minus r2, etc. So what we have done is we have solved these analytically in the E mu AQ parameter space, which is eccentricity, inverse lattice spectrum of the black hole, spin of the black hole, and Carter constant, which is constant of motion in Kerr spacetime. So what is the importance of this trajectory solution is that if they are very computationally faster, they are written in terms of standard elliptic integrals, and they are for the most generalized cases, non-equatorially centric. And they also solve the singularity problem at the turning points, which you can see that R is having R minus R1, R minus R2. And at turning points, which are R1, R2, the integrals are going to blow up. So our solution actually solved this problem by using E mu AQ parameter space. So moving to the bound orbit condition, we have derived them in both energy angular momentum space, which is on the left side, and this delta region that you see bounded by a few curves is the region of bound orbits. And the same delta region is shown as a blue shaded region in E mu space, where the red curve is that separatrix orbit, which I had shown earlier, and the S is a special orbit, which is innermost stable spherical orbit. M is marginally bound spherical orbit. So we have derived the bound orbit condition in both spaces, and we also translate them in both the parameter spaces. And then this innermost stable spherical orbit, which is basically telling what is the last stable orbit in spherical case and the marginally bound case. So we found that these are 8th order and 9th order polynomial, and they can't be solved further. RS is the radius of the orbit, and you can see these beautiful pictures. This red is the event horizon, blue is marginally bound orbit, and black is innermost stable spherical orbit. And then the final category, which is separatrix orbit, they are very important because when an orbit is in spiraling mode and then it goes to the plunging mode, it has to pass through separatrix. So if you look at on the right side, it's a potential diagram, and RS is that unstable point. So that unstable point is on the left-hand side shown as that spherical kind of point, which is the periastron point of the orbit. So if it perturbs, it will either just plunge onto the black hole, or it will come out. So for these orbits, we have derived a trajectory solution, and we found that there's a beautiful solution in logarithmic and trigonometric as a function of logarithmic and trigonometric functions. So we have the equations for these orbits, and they're very important in the study of GW in extreme mass ratio in spiral, and we have exactly found the formula for eccentricity and inverse lattice rectum for these orbits. And then finally, we have these equatorial eccentric orbit and spherical orbits. For these also, we have trajectory solution formulae. And we also extended the famous formula of Barty in 1972 to the spherical case. And then finally, fundamental frequencies, which are important in the study of QPOs and other X-ray periodicities. So we have the formulae for most general case, non-equatorial centric. And to summarize, all these analytic results have made advancements to various orbital study done by Bardeen, Schmidt, Jana Levin, Fujita, etc. And these formulae have already been used for various astrophysical applications. So this analytic framework is now utilized further to understand observation of black hole systems. And that's the second part of my thesis. So this is published in APJ, and where we study the origin of quasi-periodic oscillation in black hole X-ray binaries. So black hole X-ray binaries are a binary system with a stellar mass black hole, and it is with a binary system, it's in binary with a main sequence star. So if we look at the Fourier power spectrum of X-ray light curves, what we'll see is the broad peaks at high frequency. So on the right-hand side, you can see a power spectrum for GROJ 165540. So you can clearly see 300 and 450 hertz QPO. And you can also see, you will also find low frequency QPO, which are usually less than 30 hertz. So to explain the origin of these QPOs, we have developed this model, which is generalized relativistic precession model. So this was previously done for circular and equatorial trajectories. So what we say in this model is that high frequency QPO, the highest one is actually the azimuthal frequency of oscillation of matter around Kerr black hole. And the second high frequency QPO is the periastron precession frequency. So what is periastron precession? On the left-hand side, you will see that if a particle starts from point A and it completes a radial cycle, it will not come back at A. It will move to B. And this shift is the periastron advanced by delta phi. This is called periastron precession. The frequency of this precession is mu phi minus mu r. And then the low frequency QPO is basically explained by nodal precession, which you see on the right side of the figure. So this is basically oscillation in vertical direction. So if in a plane orbit starts at point A and it completes one radial cycle, it shifts by delta phi again, and that's called nodal precession. So we have studied various orbits, non-equatorial eccentric, spherical, and equatorial eccentric, which we show as EQ, Q0, and E0. They are just their name. So we have studied 5 cases of X-ray binaries, which are listed down. So I'm showing one case, which is emitted to X1. We clearly found one eccentric and non-equatorial solution for this, and spin of the black hole was found around 0.29. So on the top, you see the probability contours in parameter space, and on down is the probability density plot. You can clearly see the solution is at some non-zero eccentricity, and Carter constant is also non-zero, which is telling that the solution is non-equatorial. And these are all the results for all these X-ray binaries. Various solutions were found: non-equatorial eccentric, spherical, and equatorial eccentric, and etc. And all these solutions were found near the innermost stable circular orbit. And then we also compared it with the GR fluid model, where they have studied the fluid flow around the Kerr black hole. And what we found that QPOs are actually originating from a region very close to ISCO, and the edge region can be a launch pad for the instability to oscillate with fundamental frequencies, causing these geodesic flows, these trajectory flows near the black hole. So this is the final picture. So what we found is that the solution that we have, if we take a combination of parameter within the error bar that we see in this particular table, and I take various combination of parameter within the error bar, I'll find this torus picture. This is basically telling that this is the torus region where the QPO are originating, and down is the cartoon plot for our model, where we say that the edge region is basically launching the plasma blobs in this non-equatorial kind of trajectories, and this torus region is actually the origin of QPOs. And then the final part of my talk. So this is another model which we have developed for PSD shape seen in AGN. First, we have also applied this QPO model GRPM to one of the narrow line Seyfert 1 galaxy. So this is one at 0707. It showed 2 simultaneous QPOs in X-ray light curve. So we found a circular solution for this, circular orbit solution, and spin was found to be very small, 0.06, and the radius of origin of QPO was around 8.2. Now the final part, the relativistic orbit model. So we see that if we look at X-ray power spectral density, it is having a characteristic shape for narrow line Seyfert 1 galaxies. So it's having a break frequency shown by a vertical line, and below the break frequency slope is 1, and above break frequency the slope is greater than 2. How do we explain this characteristic shape? So for this, we developed this model where we assume a power law distribution of mechanical energy in the inner corona region and outer corona region. Inner is inside ISCO, outer is outside ISCO. And then we normalize this distribution and translate it to the frequency space, because we have frequency formulae. And then we generate the power spectrum. So for various combination of spin and Carter constant, we found that the slope of the power spectrum can be around 1 and 2, and these are the plots for simulated power spectrum that we generated, and we can clearly see a break shown by a vertical line at the ISCO radius. And this is the unified picture. So we say that the origin of QPOs is near the edge region, and there are non-equatorial orbits in the inner corona which are leading to the high frequency range of the PSG, and the low frequency range is coming from the accretion disk, and there is a break frequency at innermost stable circular orbit, and the QPOs are also coming from this edge region. This is the conclusion. So to conclude, we have first used the fundamentals of general relativity to study various kind of orbits. Then we developed a model for QPOs in X-ray binary, and we also apply this model to AGN, and then we have developed a model for power spectral density shape, which is ROM model. And for future, we are also studying various 3D periodic orbits, and we are trying to quantify them in the energy angular momentum space. These are the publication. Thank you.
Yeah, judges, please go ahead.
Shall I ask a question?
Yeah, please go ahead.
Prerna, thank you. Nice talk. I wanted to ask you, spin, black hole spin, at least for the supermassive black holes, is often, it's found from the iron line, FEK line, right?
Yes. Yeah.
And you are, so how do your results match with that?
Okay, so one thing is that they have an assumption that the emission is actually coming from innermost stable circular orbit, and that creates systematic to the method, and that will always give a bias that the spin is always very high through that method. So that bias is there in that method. We don't have that bias. We assume that it can be anywhere from 0 to 1. And so in that way, these results are better. So we will not have always high spin value. So there is a biasness there, that's what I'm saying.
Okay, thank you.
Okay, so any other question? Okay, so Bhalchan, can we conclude this session?
Yeah, Indulekha has her hand raised up. Indulekha wants to ask a question.
Okay, please.
Prerna, you put that limit at 30 hertz, greater than 30 hertz and less than 30 hertz. Do you have any statement regarding kilohertz QPUs?
Yes. So high frequency QPUs are basically kilohertz QPUs. So I had just shown. So that limit is coming from observation itself. It's not theoretical limit. So this 450 hertz or 300 hertz, which are observed for GROJ, they are kilohertz QPUs.
Okay. What about harmonics?
So when I say these frequencies, they are basically the fundamental frequencies, but harmonics of these are not considered in this model. These are fundamental frequencies which should be dominated in the X-ray light curve.
Oh, thank you. Nice one.
Okay, so let us conclude this. So thank you very much, all the speakers, and of course, all the judges also.
Thank you.
Okay.
Yeah, thank you.
Thanks, Bhalchan.
Thank you. Thank you, everyone.
Hi.